Hello friends, in many problems more than one mode of heat transfer may be important. There may be conduction together with radiation, there may be convection together with radiation, and these two modes of radiative heat transfer and conduction or convective heat transfer may be coupled to each other. That means they affect each other and they may be independent of each other. In that case, we may solve the problem of conduction and radiation or convection or radiation independently. So, in this lecture we will study how the conduction and radiation problem can be solved together. We will also study how the convection problem and radiation problem can be solved together. So, there are many applications. For example, in space, the spacecraft has to dissipate heat generated within the spacecraft. The heat transfer within the spacecraft is mainly governed by conduction, while the dissipation of heat from the surface of the spacecraft is mainly governed by radiation. Such spacecrafts, the dissipating surfaces of these spacecrafts are normally pointed away from the sun. So, we can safely assume that they are not irradiated by any emission outside the spacecraft. The solar radiation or any radiation coming from outside can be neglected. So, these surfaces dissipate heat through radiation into the atmosphere or into space, and energy transfer within the surface of the spacecraft is governed by conduction. Similarly, there may be some cases where, for example, in many applications related to combustion, where convective heat transfer takes place inside some tube or a combustion chamber, while the surfaces radiate the energy into the environment and leads to heating or cooling of the wall. So, first we will study the conduction and surface radiation. We take an example of fins which is typically used to dissipate heat in spacecraft. In this case, we have taken a special configuration. We have actually symmetric configuration, radially located fins around a tube. The fins have what we call a rectangular cross section. The rectangular cross section of the fin have thickness 2t. The thickness of this rectangular cross section of the fin has 2t. We will make certain assumptions as is customary in many conduction problems. We assume that the temperature of the fin varies in radial direction only. That means the temperature is not a function of theta, that means it does not vary from fin to fin at a given radial distance, and it also does not vary in the axial direction. The axial direction is rather taken very long. We assume that the end losses from the tip of the fin are negligible by convection as well as radiation. The conductivity of the material of the fin is known and is constant. The base temperature of the fin, so we have this fin which is radiating energy from both the surfaces. Here we do not have energy, so we have assumed that the end losses are negligible and the base temperature is maintained or held at constant temperature equal to Tb. There is also no external irradiation, that means the solar energy is not falling onto this fin and the space is at very low temperature, approximately close to 0. So, there is no radiation coming from the space also. Okay. We also assume that the surface of the fin, the radiative properties are gray, diffuse, and the fin itself is opaque. So, we write down the energy balance for a cross section of fin. So, we take this cross section of fin and we write down the energy balance for this fin. So, basically what we have is energy coming in through conductive heat flux and energy going out through conductive heat flux, and then from the surface we have energy leaving the fin through radiation. So, we write this energy balance equation. So, the equation is energy coming in through conduction is equal to energy going out through conduction and radiation combined. Now, we intentionally chose the thickness of the fin as 2T, the factor 2 basically cancels out. So, we get this differential equation d square T upon dx square. So, temperature is varying only in the direction, radial direction of the fin, and the radial direction here is represented by coordinate x. So, d square T upon dx square is equal to 1 upon Tk Qr, where Qr is the radiative heat flux that we need to solve through radiosity relation. Now, in this problem we see that the problem is going to be a coupled problem. Why coupled? Because in conduction equation we have a radiative source term that is appearing. So, conduction equation, this is conduction equation where we have a source term for radiative heat flux. Okay. Similarly, in the radiative equation, the radiative equation is written by, as we have already developed for gray surfaces. So, Qr, the flux at any location x, we are talking about two fins. So, if you look at the configuration of this geometry, there will be radiative heat transfer between two adjacent fins. Okay. So, we call one fin aligned in the x direction as x1 and another fin which is adjacent to it is x2. Okay. And due to symmetry we do not have to worry about the fin on the other side. So, there will be exchange of radiation between two adjacent fins. So, we have introduced a radiosity J1, okay, which depends on radiation on adjacent surface, okay, and we have emission from the surface. Okay. Now, because of the unknown temperature of the fin T, the problem is coupled to the conduction. Okay. So, we have an unknown temperature T1 which is the temperature of the fin surface at any location x1, which is linked to the conduction equation. So, this is the you can call it radiation equation. Okay. So, definitely this type of problems are very difficult to solve analytically. So, we have to solve this especially because of the dependence of radiative flux on radiosity, which is continuously varying with x. This will give us again a Fredholm type of integral equation which we know how to solve using numerical methods. So, the combined coupled problem is going to be much more difficult. So, the boundary condition we have is temperature of the fin at x is equal to 0, that is at the base is constant Tb, and the end losses are negligible. So, dt by dx at x is equal to L is equal to 0. So, this is the boundary condition for the conduction problem. A two dimensional conduction problem requires two boundary conditions. Second order boundary equation requires two boundary conditions. So, these are the two boundary conditions for the conduction problem. So, we will not attempt to solve this problem because it is very difficult to solve this problem analytically. We will just leave the development of the problem by giving a non-dimensional form of these equations. We define a non-dimensional temperature as temperature of the fin at any location x divided by its base temperature. So, this is the non-dimensional temperature theta, where theta is basically a non-dimensional length x by L. Non-dimensional radiosity is defined as actual radiosity at location x divided by black body emissive power at temperature Tb, and then we define one parameter, non-dimensional parameter n subscript c. In the numerator we have the conduction term, where we have k conductivity times thickness, half thickness T, and in the denominator we have a radiation term sigma Tb power cube L square. Now, this particular non-dimensional parameter is often called Planck number, which is basically a ratio of conductive heat transfer to radiative heat transfer. Now, with this non-dimensional parameters we can write our equations, the conduction equation as this is our modified non-dimensional conduction equation. So, non-dimensional temperature d square theta by non-dimensional length d zeta square is equal to 1 upon Nc epsilon over 1 minus epsilon theta power 4 minus radiosity, non-dimensional radiosity. So, of course, this is a non-linear equation and has to be solved using numerical methods. The non-dimensional radiosity relation can be written. We have already discussed how to evaluate this in case of gray surfaces. So, we have what we call emission term, theta is unknown here. So, it is coupled to the conduction problem, and we have this function what we call kernel function that depends on the view factors and all. So, this is for the irradiation term or absorption. Okay. So, this becomes an integral equation. So, we have to solve these equations, conduction equation which is non-linear, and radiation equation for radiosity which is basically integral equation. So, both the equations are difficult in their own sense and have to be solved using some kind of numerical scheme. The boundary conditions, the modified boundary conditions in non-dimensional parameters becomes theta is equal to 1 for zeta is equal to 0 and d theta by d zeta is equal to 0 for zeta is equal to 1. Now, just like we define fin efficiency in case of conduction and convection combined mode heat transfer, we also define fin efficiency for conduction and radiation. So, the fin efficiency is defined as heat loss, actual heat loss from the fin divided by an idealized situation where we have a black fin at an isothermal temperature Tb. So, if such a idealized fin exists, then the heat loss from that fin, we compare our actual heat loss from that fin, and the ratio is basically defined as the fin efficiency. Why we have taken denominator as black fin and isothermal fin? Because black surfaces basically radiate the maximum amount of energy. So, the fin will be most efficient when its temperature will be highest, when its emissive power will be highest, that is black body at isothermal temperature Tb, that is going to give us the maximum amount of energy emitted by the fin. So, that is why we have taken it in the denominator, and the denominator can be evaluated analytically. It will be basically equal to sigma T to power 4 1 minus F12, because some part of the radiation will actually be interchanged with the adjacent fin. So, the factor 1 minus F12 appears because of that geometric configuration. So, this is our heat loss from idealized fin or black fin at constant temperature Tb. Okay. Now, heat loss from the actual heat loss can be calculated in two ways. Once we have solved the problem, the conduction and radiation problem, we know radiative heat flux as a function of x, we know temperature as a function of x. So, either we can solve for dt by dx once we know t as a function of x and calculate the actual amount of heat transferred by calculating the gradient dt by dx at x is equal to 0, or we can basically integrate over the radiative heat flux from 0 to L. Both the integration will give you the same results, okay, and this will appear in the numerator, and the ratio is defined as the fin efficiency. So, as I said, these problem can be solved numerically, very difficult to solve analytically. I am showing you here one figure that basically explains how the efficiency of the fin varies. On this chart we see that the efficiency is going to decrease when the fin goes from black to gray. Okay. If the emittance is 1, that is the fin is black, the efficiency is highest, and if the emittance is less, let us say 0.5, the efficiency is going to go down, and the reason is already explained, because the black surface emits most amount of the radiation. Similarly, the fin efficiency decreases with 1 over radiation the Planck number. So, 1 over Nc is the inverse of the Planck number, Nc is the Planck number. So, the radiative efficiency of the fin decreases with this number. Now, the reason is, let us say if you have highly conducting fin or the value of k is large, then 1 over Nc is going to be very small, the conduction basically dominates, the fin will be isothermal, and the efficiency of the fin is going to be large. Okay. So, with the radiation number, with Planck number, 1 over Planck number, the efficiency of the fin decreases. Okay. So, numerically this type of problems can be solved. We will not attempt to solve any example analytically in this lecture. Next we will discuss is combined mode convective and radiative heat transfer. In combined mode convective and radiative heat transfer, the surface radiation from a surface, this could be internal flow, let us say flow through a pipe where the surface of the pipe is heated with constant heat flux as is shown here, or it could be external flow over a flat plate where the surface of where the plate surface is heated with constant temperature or constant heat flux. Okay. Now, due to radiation emitted from these surfaces, either the plate surface or the pipe inner surface, the heat absorbed by the fluid is going to change. Okay. Because some amount of energy is lost due to radiation, the temperature of the fluid or the temperature of the wall of the pipe or flat surface is going to change. Okay. Now, in this particular configuration, the fluid enters a pipe with a mean temperature of Tm1 and it exits the pipe with a mean temperature of Tm2. Now, the surface on the left hand side, the pipe inlet surface or inlet circle is exposed to environment maintained at temperature T1. It could be like this. We have basically let us say some kind of furnace and we have some environment and the pipe basically takes some kind of fluid, okay, and this fluid basically takes fluid to the discharges the fluid to some environment maintained at temperature T1. Okay. So, the two ends of the tube are going to be at different surfaces. Okay. Now, what we have basically assumed here is that the fluid itself does not absorb radiation, that is it is non-participating medium. If the fluid absorbs radiation, then definitely radiation will increase the temperature of the fluid, but here we are assuming that the fluid is non-participating radiatively and the only role of radiation is basically heat loss from the ends of the pipe. So, we write an energy balance equation for a small elemental volume, let us call this elemental volume dV. Okay. We write energy balance for this volume. Okay. This is the boundary conditions that we will apply. I have already explained this. This is constant heat flux problem. The tube surface is maintained at constant heat flux QW while the temperature of the surface is changing with respect to x. So, both Tm is a function of x and Tw, that is the wall temperature, is a function of x. Okay. And the heat transfer coefficient is assumed to be constant. So, we assume that heat transfer is not varying with the pipe length. So, writing the energy balance equation, we take elemental volume dV. So, in this we have enthalpy coming in which is equal to mCp, this is enthalpy coming in mCp and the bulk fluid temperature Tm and enthalpy going out which is mCp and the temperature is going to be changed. Here let us say temperature is Tm, here temperature is Tm at x plus delta x. Okay. So, the temperature is changing along the pipe length. So, the enthalpy is going to change and then we have heat added or removed from the wall through convection. So, the heat transfer coefficient is H and this is the temperature difference between wall and the fluid. So, Tw minus Tm, this is the amount of heat removed per unit area from the wall surface and we multiply by the contact area of this fluid element which is basically equal to 2 pi r and this thickness dx. Okay. So, this is the total amount of heat removed by this small element from the surface of the tube. Okay. Now, as I said, the fluid is non-participating, so no radiation term comes in this. So, radiation basically comes into this equation through temperature only. So, we can write down this equation simply dt by dm by dx. So, we expand this right hand side with the Taylor series and we can write down the differential equation. The derivative of mean bulk temperature of the fluid at any location x dTm by dx is equal to 2h by rho Cp UMR, where UM is now average fluid velocity and rho is the density of fluid, where r is the radius of the pipe. Okay. So, we can write down this differential equation. Now, same type of energy balance we do for the surface element of the pipe, that is this surface element, this is the pipe surface, the small element dx. Okay. The area of this element will be of course 2 pi r dx. Okay. So, the heat removed or the heat flux on the wall surface QW, assuming it to be gray, will have a radiation component, emission minus absorption term, absorption of radiation coming from the two ends as well as absorption of radiation coming from other part of the pipe. So, the radiosity contains three components: radiation coming from left end, radiation coming from right end, and radiation coming from other parts of the pipe. And then we have also heat flux due to convection. So, heat removed from the pipe surface contains two components, one is convection, which is actually taken by the fluid, and one is radiation, which is not taken by the fluid because fluid is not participating, it is basically lost to the environment. So, the expression for radiosity Jx contains emission and the reflection part, this is the reflected part, where the term in the bracket basically includes comprises of irradiation. So, the fluid surface is basically irradiated by surface from inlet, outlet and other parts of the surface of the pipe. Okay. So, there are three components of irradiation: irradiation from outside radiation, surface inlet surface 1 and inlet surface 2, and irradiation from the pipe itself. Okay. So, that will be basically an integral equation because radiosity is varying along the pipe surface. So, again this problem can be solved using numerical methods, where we have to solve one integral equation, the Fredholm equation, and one equation we have to solve is for convection, which is basically linear equation. So, these two equations we have to solve. We non-dimensionalize the problem, we define a non-dimensional length x by d, we define non-dimensional temperature or non-dimensional temperature as sigma T power 4 upon QW power 1 by 4. We define non-dimensional radiosity as J by QW, where QW is a known constant, that is the heat flux at the wall. Then Stanton number is defined as H upon rho Cp UmD, and one more non-dimensional number we define for the heat transfer coefficient, H is equal to small h by QW times QW by sigma power 1 by 4. Okay. So, these non-dimensional numbers we have defined, and based on these four non-dimensional numbers we write our governing equation. So, the first equation for convection becomes d theta m by d xi, where theta m is now the non-dimensional temperature, is equal to 4 times Stanton number non-dimensional wall temperature theta w minus non-dimensional bulk temperature theta m. Okay. So, both theta w and theta m are unknown here. Then from radiative energy balance we can write down equation 1 is equal to h theta w minus theta m, epsilon over 1 minus epsilon theta 1 power 4. Now, theta 1 is known, it is the temperature at the inlet minus radiosity, non-dimensional radiosity, and then we have non-dimensional radiosity, which can be written as non-dimensional emissive power epsilon theta w 4 and emission term or irradiation term from the inlet ends and irradiation from the pipe, other part of the pipe. So, this is the integral equation in non-dimensional form. So, these equations we have to solve using some kind of numerical scheme. The problem is a coupled problem because the temperature, the unknown temperatures Tm and Tw appear in both convection and radiation equation. We conclude this lecture by showing you the results It is very difficult to solve this problem analytically, but it can be solved through numerical procedures. So, what I show you on this slide is basically the result for non-dimensional temperatures, wall temperature and bulk fluid temperature with the axial non-dimensional axial length. So, we expect that the fluid temperature will increase, as is also observed. The fluid temperature increases with the axial length, because the fluid is going to absorb energy from the wall through convective heat transfer. So, fluid temperature will continuously increase. What is surprising is the distribution of wall temperature, how the wall temperature basically varies. If we do not include radiation into effect, then we find that the temperature should also increase, the wall temperature should also increase, because we have supplied constant wall heat flux and the bulk fluid temperature is increasing. So, the wall temperature should also increase, and it is clear that the wall temperature is indeed increasing, and rather linearly it is increasing. The increase is significant for larger L by D ratio, while the increase is not very significant if the pipe is short. For long pipes, this is going to have significant increase. What is surprising and what is interesting to observe in this image is the variation of wall temperature when radiation is taken into account. So, we see that radiation basically leads to loss of energy from the pipe surface, and we expect that the wall temperature should come down. Because of this loss of energy, the wall will be cooler as compared to when radiation is not taken into account, and this is pretty much clear, where for all values of L by D 1, 10 and 50, the flux is significantly less than the flux value without radiation. Okay. The decrease is highest in pipes with L by D ratio of 1, and the reason is for shorter pipes. So, this is let us say L by D equal to 1, this is L by D equal to 10, and this is L by D of 50. Okay. So, for L by D, the fraction of radiation energy loss, because now the surface is pretty much exposed to the ends of the pipe are very close to the surface of the pipe. So, the refraction of energy lost by radiation is much more significant for smaller pipes. Okay. So, here radiation losses are significant, and we can see that the temperature difference with and without radiation is highest for the case L by D equal to 1. Here in L by D 50, radiation is still there, but it is mostly confined to the end regions, and we see that the temperature drops significantly in the end regions. Okay. There is a significant drop in temperature in the end regions, but in between, the difference between the temperature with and without radiation is not much. Okay. Because radiation effect is hardly observed in the middle of the pipe, while at the ends radiation is significant, and it leads to significant reduction of radiative significant reduction of wall temperature at the end of the pipes. So, I conclude this lecture where we have discussed combined mode radiative heat transfer. The problem are coupled and normally governed by Fredholm equation. So, the analysis of these type of problems have to be done through numerical analysis. In the next lecture, we will discuss problems where radiation passes through a medium where the medium is not vacuum, rather the medium is emitting, absorbing and scattering medium. Such problems we encounter in large number of applications like combustion, furnaces, atmosphere. So, thank you for the time being. We will see you next time.